Welcome, everyone, to this explainer. So, you know how we usually think of Earth as just a passive launch pad? Like a quiet, stable piece of ground you simply leave behind when you head into space? Well, I need you to completely rethink that picture. Earth is actually this incredibly active, multi-layered obstacle course. It's literally an invisible gauntlet that every single spacecraft has to survive. Today we're going to break down exactly what that gauntlet looks like and why simply getting out of our own neighborhood is, for sure, one of the greatest engineering challenges in human history.
Okay, let's dive right into this. Does space really start empty? I mean, most of us probably imagine that the moment you leave the ground or, clear the clouds, you're immediately in this pristine, crystal clear void of outer space. We picture rockets just floating peacefully, kind of like in a sci-fi movie. But the reality is way more complex. Earth's environment extends far beyond its surface, surrounding the planet with intense forces that directly dictate how we design, launch, and operate space vehicles. Long before a spacecraft can gracefully coast among the stars, it has to aggressively fight its way through the unseen, powerful physical properties of our home planet.
So here is our mission briefing for today. We're covering escaping Earth's gravitational grip, surviving the atmospheric gauntlet, navigating the magnetic shield, battling the planetary oven, and finally, designing for the environment.
Let's start with Part 1, Escaping Earth's Gravitational Grip.
The very first invisible hurdle any spacecraft faces is, without a doubt, gravity. It's the absolute dominant force acting on a vehicle before launch, and honestly, it continues to dictate its life while in orbit. You can't ignore it, and you certainly can't turn it off. Newton's law of universal gravitation illustrates this beautifully. If you think about that math, specifically that r² component, the distance from Earth's center, it tells us something crucial. As a rocket gains altitude and moves away from the surface, that gravitational pull doesn't just suddenly switch off once you cross some imaginary line into space. It only gradually decreases. You are physically fighting that mathematical reality every single inch of the way up.
Right down here at the surface, that pull translates to an acceleration of 9.81 meters per second squared. That number right there, that is a massive physical anchor tying us down. It's the exact primary reason why rockets require such extreme, violent thrust just to get off the launch pad. I mean, you have to overpower that 9.81 meters per second squared before the vehicle can even budge a single millimeter.
Because of that anchor, the ultimate engineering cost of gravity is staggeringly steep. It strictly determines our launch vehicle's overall performance, it dictates the escape velocity we need to break free, and because of that, it defines the absolutely massive amounts of total propellant required. But it doesn't stop at launch. Gravity is the primary factor in our orbit selection and ultimately decides the orbital lifetime of a spacecraft. Basically, gravity is the boss, and every single mission budget and design revolves entirely around it.
Moving on to Part 2, Surviving the Atmospheric Gauntlet.
So once you're actively fighting gravity with all that massive thrust, you simultaneously have to push through physical friction. The atmosphere extends several hundred kilometers above Earth's surface, acting as this thick and then gradually thinning soup of gases that the spacecraft has to literally tear through. Now at rest, this familiar mix of 78% nitrogen and 21% oxygen is totally harmless. We breathe it every day. But for a spacecraft accelerating at thousands of miles an hour, it becomes a literal physical wall. Punching through this gas causes severe aerodynamic drag. It causes intense aerodynamic heating, literally baking the exterior of the rocket, along with brutal wind loading and massive dynamic pressure during launch. It's just a physical beating. As a rocket ascends, it punches through some very distinct layers. Starting down in the troposphere, from 0 to 12 kilometers up, you've got weather, clouds, and most of the atmospheric mass. This is exactly where almost all your frustrating weather-related launch delays happen. Then you pass through the relatively stable stratosphere up to 50 kilometers and the meteor-burning mesosphere up to 85 kilometers. But think about the thermosphere for a second, extending all the way up to 600 kilometers. The air up there is extremely thin, sure, but it still contains residual atmospheric particles. Over time, those tiny particles produce enough aerodynamic drag to slowly decay the orbits of low Earth orbit satellites. It really isn't until you reach the exosphere, above 600 kilometers, that you finally experience that true gradual transition into outer space.
Part 3, Navigating the Magnetic Shield.
Okay, so you've survived the crushing gravity and you've pushed through the physical drag of the atmosphere, only to enter an invisible web. Earth behaves exactly like a giant magnetic dipole, which creates a protective shield known as the magnetosphere. Now, you might naturally think that invisible magnetic fields interacting with a metal spacecraft would be a pure hazard. And they certainly can be. Interactions between the magnetic field and spacecraft materials generate these disturbance torques that mess with the vehicle's orientation. But engineers actually flip this hazard into a major advantage. Step 1, they use it for attitude determination, basically treating the Earth like a giant space compass to figure out which way the craft is pointing. Step 2, they use magnetometer-based navigation to help guide the ship. And Step 3, which is just brilliant, they actually use magnetic torque rods on the spacecraft to push against Earth's magnetic field. This allows them to physically control their attitude and steer without expending precious thruster fuel. How cool is that?
Which brings us to Part 4, Battling the Planetary Oven.
When most people think of space, they picture bitter, freezing cold. But in low Earth orbit, you're actually battling immense heat, and it comes from two very distinct mechanisms. First up is Earth's albedo. See, not all solar radiation gets absorbed by Earth. About 30% of it is reflected right back into space by our clouds, our oceans, the ice, and the land. This acts like a giant mirror, blasting low Earth orbit spacecraft with a huge amount of additional reflected heat. And then you have Earth's infrared radiation. After absorbing the sun's energy, the Earth continuously emits thermal energy in the form of infrared radiation. Unlike direct sunlight, this is continuous. So the absolute kicker here is that thermal engineers have to design a spacecraft's control systems to survive not just the burning direct sunlight, but the blinding reflection of the albedo and the relentless, radiant oven-like glow of the Earth itself.
And finally, Part 5, Designing for the Environment.
We've mapped out the full gauntlet now, and we can really see how these unseen forces literally write the entire aerospace engineering rulebook. I mean, every single subsystem is a direct response to this environment. Gravity forces us to build massive propulsion systems just to meet launch energy requirements. The atmosphere demands specific structural loading parameters and thermal protection just to survive the drag and heating. The magnetic field, it acts as our compass and steering wheel, even as it constantly tries to twist the spacecraft with those disturbance torques. Our planet's albedo and infrared radiation command our thermal radiators, dictating exactly what materials we use to maintain a thermal equilibrium. And of course, that pesky residual atmosphere means we have to constantly calculate and correct for the orbital decay of our satellites in low Earth orbit.
So I want to leave you with something to really chew on. If Earth's environment, our own, familiar home, the place we are most perfectly adapted to, is this complex and this demanding, what in the world is it truly going to take to design spacecraft for the extreme alien environments of other planets? Just surviving our own planet's invisible gauntlet is a monumental, awe-inspiring achievement of engineering. Seriously, keep that in mind the next time you watch a rocket launch. Thank you so much for joining me on this explainer. I hope you found it as fascinating as I do, and as always, keep learning.